The task: determine all pairs of positive integers n and k for which n factorial plus n equals n to the power of k holds. This task was proposed by Michael Reitmeier. Good task. Right, so what do we do? First of all, we see that factorial and n to the power of k is fast-growing functions, so we try by hand different n. Up till 5, we get the following pairs: 2, 2, 3, 2, and if n equals 5, then k equals 3. Then, if we start to get greater n, things starts to get ugly, very quickly. N equals 6, 7, 8, and 9, and 6 and 7 you can really check, but up from 8 and 9 and 10, the factorial numbers are very big and it will be very hard to get them. So the intuition says that only this really should be the answer, and no other numbers, no other pairs should exist. And this is what we need to try to prove. For this, we need algebra. First of all, we obviously reduce everything by n, and we get this expression: n minus 1 factorial plus 1 equals n to the power of k minus 1. What do we see here? Our left-hand side has n minus 1 factorial. So everything, including n minus 1 and below, divides n minus 1. So n minus 1 factorial is divisible by 1, 2, 3, 4, and everything less than n minus 1. But if we add plus 1 to this, plus 1 is not divisible, is divisible by nothing. Neither by 2, nor by 3, nor by anything. So, left-hand side of our equation is not divisible by 2, not by 3, not by 4, not by 5, not by anything until n minus 1. So should be the left part as well. N should not be divisible by n minus 1, n minus 2, and so on, by 3 and by 2, by everything. It can only work when n is a prime number. So all non-prime numbers are for n are excluded automatically, but n should be prime. We basically need here to try to exclude this one as well. So let's continue with the algebra. We put 1 to the right, and we have n times k minus 1 minus 1. What is this? This is something, looks like geometric progression to me. We can apply the formula, so it becomes n minus 1 times the adding series of progression, starting from a small number, plus n squared, and so on, n to the k minus 1, n to the k minus 2, the big sum. And we can even reduce it further by n minus 1. So we get n minus 2 factorial equals this sum. For what do we need to think further? We need to try to divide it, maybe we should find some factor by divisibility by which would be hard. So n minus 2 factorial, that's how we basically solve our number theory problems. N minus 2 factorial is divisible by everything below n minus 2 and including n minus 2. So by 2, by 3, as I told you before. Therefore, it is dubious if it is divisible by n minus 1. And this is what we need to answer. What can we use here? That n is a prime number. So p minus 1 is, since n is big enough, it's certainly greater than 2. Much greater even than 5. Then n minus 1 should be both even number and not a prime, obviously. Yes, so this number, what can it be? It should be really, if it is not a prime number, how many factors can it have? It can really, like n minus 2 factorial, it has everything, all the factors below n minus 1. And looks like if n minus 1 is something times something, then like a times b. And if a and b are distinct numbers, then look, these numbers are obviously included into the elements of factorial n minus 2 factorial. So let us check this. We see that when can it not work that n minus 1 equals a times b and a is not equal to b? It cannot work only if n minus 1 is a product of some, is a square of some prime number. But it cannot be the square of any prime number because it is an even number. So if it is divisible by 2, then considering it's a complete square, it should be divisible by 4, and our prime cannot be 2, whose square is supposedly n minus 1. Therefore, n minus 1 can be represented as the product of two distinct numbers a and b. A is not equal to b, and therefore n minus 2 factorial is divisible by n minus 1. So then we can rewrite this expression modulo n minus 1. So the left hand side is divisible by n minus 1, so we write it 0 as we proved. The right hand side, so each number n is divisible. When we divide it by n minus 1, we get the remainder of 1 to the power of like k minus 1, k minus 2, that's what we write. But since it is all 1, then we have 1 plus 1 plus 1 plus 1, and this happens k minus 1 times, and so it equals k minus 1. So 0 equals k minus 1 modulo n minus 1. Therefore, from this, given that we have n big enough, we can conclude that k is greater or equal than n. And this is where we need to find a contradiction, because look, k, it appears to be very, very big number here, greater than n. But left hand side should not really be as big as n to the power of n. So n minus 1 factorial on the one hand is less than n minus 1 to the power of n minus 1, because we take not n minus 1 times, but we take n minus 1, n minus 2, n minus 3, and so on, including small numbers like 2 and 3. So on the other hand, if we look on the right hand side, n to the power of k is greater or equal, according to this proven statement, than n to the power of n, and this is greater than n minus 1 to the power of n minus 1, and this is greater, obviously, than n minus 1 factorial, even plus 1. And so we got a contradiction. Therefore, only working numbers for the answer are these pairs 2, 2, 3, 2, 5, 3. No other pairs are possible. And this finishes the task.